Okay, it gives me great pleasure to welcome Professor Nicole Younger-Halpern. Finally say that in person. So just like to tell you a little bit about Nicole's background. So Nicole, for many of you will know this, she was an undergrad at Dartmouth, and she graduated with her bachelor's in 2011, actually as co-valedictorian. I still remember the speech you gave on tensors. And so following Dartmouth College, she went to England, to the UK, and worked with a professor at Lancaster University for almost a year, I think, and also spent time in the University of Oxford. And then from there, she moved to Canada to take a master's at the Perimeter Institute and University of Waterloo. That was in 2013. And after there, she moved on to Caltech to do her PhD, which she got in 2018. And for her PhD, she won the Ilya Prigogine Prize for thermodynamics pieces. That's actually an international prize. And following Caltech, she, in 2019, went to Harvard, to ITAMP as a postdoctoral fellow. And now she's at University of Maryland and NIST. And before I leave it to you, I just wanted to just say a few words, personal words, if you like, because I've known Nicole even from before she came to Dartmouth, because I actually remember receiving an email from you when you were still in high school. I couldn't find that email, but searching on my laptop this morning in my email folders, you were here most recently enough that I still had emails from when you were an undergrad. And there was a whole stream of exchange of emails, and I realized that you did Physics 50, it's called 40 then, I think, or I can't remember the name of it, Physics 50 in your senior year winter term. So I guess you didn't decide to major in physics until almost your last year of college, or decide to do physics, quantum physics. And anyway, here's the title, Quantum Steampunk, Quantum Information Meets Thermodynamics. So it's never too late to decide to do quantum physics. So welcome, Nicole.
Thanks very much for the very kind introduction. And thank you for the invitation to speak here. It's very much a pleasure to be back. It is in large part because of people in this room that I became a physicist, and I even have a colloquium to give. So it's really a pleasure to be back in Wilder. Of course, this doesn't work again. All right, do it the old-fashioned way. So I'd like to begin with a technical term, steampunk. Steampunk is a genre of literature, art, and film. Set in the late 19th century, it encompasses all of the romanticism of the Victorian era, then cranks up the technological level to 11. Steampunk features old settings from the 1800s, like the earliest factories and men in top hats, together with futuristic technologies like time machines, airships, and robots. There's this fusion of the old with the new that creates a wonderful sense of adventure and romanticism and nostalgia. So people dress up in these steampunk costumes and go to steampunk conventions. But I like to say, they dream it. Quantum information thermodynamicists live it. But let me break down that term. Thermodynamics is the branch of science that covers energy, the different forms that energy can be in, and the transformations amongst those forms. It was developed during the 1800s, the steampunk era, because the steam engine was revolutionizing industry, and people wanted to understand it. How efficiently could we pump water out of mines? These practical questions led to fundamental questions like, why does time flow in only one direction? Thermodynamics was developed to describe the cutting edge technology of the day, the steam engine, so a large classical system. Today's cutting edge technology looks a little bit different. We have great control over small systems. For instance, this is a strand of DNA. You can trap the ends of it using an optical trap and use optical tweezers to stretch the strand. And then you can measure the work required to stretch the strand through a given distance. Of course, many of us are interested in quantum settings. For instance, this is a dilution refrigerator that Google uses to cool down one of its quantum computers formed from superconducting qubits. You need to have the superconducting qubits at low temperatures for them to be superconducting. And cooling to low temperatures is a thermodynamic process. Relatedly, we're interested in the interplay between information and energy. And a lot of out of equilibrium systems are now under study. Apart from you and me, we as living beings are out of equilibrium. But there are also a lot of interesting quantum experiments in which people have some many particle system and whack it out of equilibrium and watch it bring down back to equilibrium. These settings are very different from the old conventional thermodynamic setting that we just saw, but thermodynamic concepts like work and heat remain relevant. So we need a toolkit for updating thermodynamics from the 1800s for the 21st century. Quantum information theory provides such a toolkit. By quantum information theory, I mean the study of how we can use quantum systems to process information in ways that we can't using just classical systems like my computer. By process information, I mean solve computational problems, communicate information, secure information cryptographically, and store information in memories. By quantum phenomena, I mean entanglement between particles, how operators don't necessarily commute with each other, the discreteness of spectra, how you disturb a system when you measure it if it's quantum, and more. Quantum information theory, in parts like thermodynamics, has been inspired by technology, such as the promise of quantum computing. But because of that promise, we now have this wonderful mathematical and conceptual toolkit that's being applied to many different spheres of science to understand them anew, such as condensed matter, black hole physics, computer science, atomic, molecular, and optical physics, and thermodynamics. So you can take the thermodynamics of the 1800s and look at it anew through the lens of quantum information. This field of quantum thermodynamics involves reimagining the laws of thermodynamics for systems outside of conventional thermodynamics, small systems, quantum systems, far from equilibrium systems, and information processing systems. In quantum thermodynamics, we ask how we can use quantum resources as we can't use classical ones. We know that we can use quantum systems to perform some certain computational tasks much more efficiently than we can use classical systems. And computation is an information processing task, just as work extraction is a thermodynamic task. So we can ask similarly, can we use quantum resources to perform thermodynamic tasks better? And in that way, we can actually learn more about the divide between quantum and classical. We also ask which features of thermodynamics truly are non-classical. This blend of old and new, I like to call quantum steampunk. Here's where I'd like to go in the rest of this talk. First, I'd like to convince you that there is some reason to put together quantum information theory and thermodynamics. Then we'll see how the two can enhance each other. We'll see that work, thermodynamic quantity, and information both can serve as resources in computation and thermodynamics. Then after that sort of broad overview, I'd like to provide a little taste of one active field of research in quantum thermodynamics, namely quantum thermal machines. And finally, I'll talk about the opportunities in this field. So why does it make any sense to use quantum information theory to re-envision thermodynamics? About this slide, so when I was making this PowerPoint, basically to entertain myself, I peppered the slides with steampunk artwork. So if steampunk is not your favorite aesthetic, then I apologize, but hopefully it will keep you entertained. A big question behind a lot of information theory is how efficiently can we process information? The answer I like to call the liver of information theory. When I was in 9th grade, I had a biology teacher who said, if you ever don't know how to answer a question on a test of mine, write down liver. The liver performs a ridiculous number of functions in the human body. So if you don't know the answer to a biology question and you write down liver, you have an anomalously high probability of being correct. But similarly, if someone asks you, what is the optimal efficiency with which we can perform some information processing task, and you answer a function of an entropy, you have an anomalously high probability of being correct. By entropy, I mean a function of a quantum state or probability distribution. It quantifies the uncertainty about the outcome of measurement of the state or the value of a variable distributed according to this probability distribution. To progress farther in this direction, we need a quick review of a few concepts in quantum information theory. One is qubits. So the qubit is the basic unit of quantum information. It's the analog of the bit, which is the unit of classical information. A bit is something that can have one of two possible values, such as 0 or 1, or left or right. Qubits manifest as quantum two-level systems, such as the spin degree of freedom of a particle that has a spin quantum number s equals 1/2, of which the electron is one example. We denote a qubit state often with this symbol rho, which is a density operator. You can think of it as a matrix relative to your favorite basis. Technically, it's a trace one, positive semi-definite linear operator. The trace one means that if you measure this state, you'll get some outcome. And the positive semi-definite means if you calculate the eigenvalues of this matrix, you'll find that they're all real and at least 0. We represent qubits with points on or in the Bloch sphere. A particularly simple class consists of pure states, which we can write as utter products. This ket psi represents a vector in a Hilbert space, and it's represented geometrically by an arrow that reaches from the center of the Bloch sphere to the sphere itself. For instance, this upward pointing arrow represents the quantum analog of a 0. This downward pointing arrow represents the quantum analog of a 1. And a qubit can be in any superposition of the two. Another class of states consists of mixed states. These can't be expressed just as outer products or just as kets. A mixed state is the state of a quantum system that's entangled with some other system. And it's represented by an arrow that doesn't go all the way out to the Bloch sphere. The shorter the arrow, the more entangled our system is. One favorite thermodynamic example is the quantum thermal state. This beta is the inverse of the temperature of our system. H is the Hamiltonian governing our system's evolution. And this partition function Z ensures that the state is normalized to 1. Okay, now that we have that in place, we can meet an entropy face-to-face. So let's see that there is some information processing task whose optimal efficiency is an entropy. So suppose that I have a message and I would like to send it to Lorenza. We agree in advance on the possible letters that I might send. And she knows the probability that I'll send an A, the probability that I'll send a B, and so on. According to her, I'm sending this mixed quantum state in which the possible letters are weighted by their probabilities. And suppose for mathematical convenience that I'm sending a large number n of copies of this state. So I'm sending a tensor product. Into how few qubits, basic units of quantum information, can I squeeze my message? I'm performing the information processing task of data compression. The answer is given to us by Schumacher's theorem, which says that in the limit as the number of copies approaches infinity, the number of qubits I need per copy of my message is the von Neumann entropy of my state, the negative of the trace of rho log rho. This quantifies Lorenza's average uncertainty about what letter I'm sending. So that's how we can use an entropy. But why is this thing that quantifies our uncertainty in information theory called an entropy? The The answer is given to us by Claude Shannon, who founded information theory. This is a Google Doodle from his 100th birthday a few years ago. But he said that John von Neumann, the great Hungarian-American mathematical physicist, told him, you should call it entropy for two reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name, so it already has a name. In the second place, and more important, no one knows what entropy really is, so in a debate, you will always have the advantage. That's why I do information theory and thermodynamics. Indeed, here's the fundamental relation of statistical mechanics. And here is the thermodynamic entropy. In thermodynamics, it signifies how spread across phase space the distribution of that we attribute to a classical statistical mechanical system is. So suppose we have a classical system of many, many particles. We don't know all their positions and all their momenta. Instead, we ascribe to them a probability distribution over all the possible sets of position and momenta. So in statistical mechanics, as in information theory, an entropy signifies an uncertainty. So that's some reason to think that it could make sense to put quantum information theory together with thermodynamics. But now let's see that they can actually help each other out. We'll show that, oh, by the way, this is perhaps my favorite lecture in P75. It is probably one of the reasons why I'm doing quantum thermodynamics, because Shekhar had a lecture on this and I was just so taken with it. I didn't know why, but I knew I needed more of it. And so I spent my life on it. This construction is called Sealard's engine. It shows that we can use information to turn heat into work. The heat is energy transferred between two systems that is random, it's uncoordinated, it's not doing anything useful, so it's not very helpful. Work is coordinated, organized energy that we can use directly to do something useful like push a rock up a hill or charge a battery. And Sealard was another great Hungarian-American physicist of the 20th century. Consider a classical particle in a box. This is going to be a very, 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 very simple model for an ideal gas. Suppose that the particle exchanges heat with a fixed temperature bath or environment through the walls of the box. And suppose that we start with one bit of information. We know that the particle is on the right-hand side of the box rather than the left-hand side. We can slide a partition into the box, then tie a rope to the partition and tie an Acme anvil to the rope. Then we can unfix the partition to let it slide. The particle is going to punch the partition. And it's going to keep punching the partition until the partition gets to the other side of the box. Now we have lifted the anvil, it's gained potential energy, so we've done useful work on it. Where did that work come from, being energy? It came from the heat bath. We converted that heat into work. How much work can we perform on average? This type of work is pressure volume work. So it's this integral. We remember from high school the form of the ideal gas law. This is the pressure, the volume, the number of particles, Boltzmann's constant, and the temperature. We can solve for the pressure in terms of the volume and then substitute into the integral. I'm integrating from V over 2 to V because the particle begins confined to half the box, but ends up able to be anywhere in the whole box. So we integrate, we evaluate the limits, and we find that the work we can perform on average is at most Boltzmann's constant times the temperature times log 2. So we can perform this amount of work, but we've lost our information. Now we have no idea where in the box the particle is. So we've traded information for work. We can go in the opposite direction and perform what's called Landauer erasure. So suppose that we begin with a lifted anvil. We have the potential to do work, and we don't know where the particle is. We want to reset it to the right-hand side of the box to a clean, well-defined position. This is analogous to taking a sheet of scrap paper that's been scribbled over and erasing it to a nice, clean, well-defined state. We can slide a partition into the box on the left-hand side, and then push the partition to the center of the box so that the particle is trapped on the right-hand side. This is the compression of a gas. That costs work, so we do need to pay work, but we've recovered our information. So we've traded work for information. This story has deep implications for the relationship between thermodynamics and computation. Suppose that we want to compute and compute and compute and compute. Eventually we'll run out of scrap paper and we'll have to erase some. We've just seen that erasure has a thermodynamic cost. So there's a fundamental thermodynamic cost to computation. When I learned this, it blew my mind, because who would have thought thermodynamics and computation seem fairly separate? Who would know a priori that they go together? But it turns out that they are very much intertwined. I've been telling you a story about a classical gas in a box, but gosh darn it, this colloquium is called quantum steampunk, so how can quantumness come in? There are a number of different ways. I'll talk about one. And to get there, we need a little bit more background. It's about entanglement. Entanglement is a relationship that quantum particles can share. It manifests in correlations between the outcomes of measurements, and these outcomes correlations can be stronger than any achievable with just classical particles. A simple example is the singlet state of 2 qubits. Loosely speaking, either the first qubit is in the 0 state while the second is in the 1 state, or the first qubit is in the 1 state while the second is in the 0. For example, suppose that Miles and I each have a particle. Sorry, Miles. You're probably not going to invite me back now. We can bring the particles together and perform some operation on them so that they become entangled, and then we can take them to the opposite sides of campus. And suppose that Miles measures his particle locally. Then he has no idea which outcome he'll obtain. For instance, suppose that we have spins, and he measures whether his particle points upward or downward. He has 50-50 probabilities of the 2 possible outcomes. Now, suppose that each of us measures his or her particle. Then there are some sets of measurements that we can perform such that we can predict something about the joint outcome. For instance, suppose that we both measure whether our particle spins point upward or downward. Then if Miles gets the down outcome, he knows I'll get the up outcome. And if he gets the up outcome, he knows I'll get the down outcome. Furthermore, there is a measurement that we can perform jointly on both particles together, such that we can predict the outcome exactly. So there's something that isn't in Miles's particle, it isn't in my particle, and it isn't in the sum of 2 separate particles. It's in the pair of particles. So I like to think of this as being the principle that the whole is greater than the sum of its parts when it comes to entanglement. Let's use that in erasure. Suppose that the system that we want to erase is not a classical particle in a box, but a qubit. And we have no idea where the qubit state is pointing. We want to erase it to the 0 state. Suppose that the qubit is entangled with some other system, some memory. And again, there's a heat bath that we can use. Then we can erase the qubit while keeping the memory's reduced state as it is and extracting net positive work. This should surprise us because we just saw that erasure costs net positive work. But we can, in a loose sense, sort of burn the correlations between the system and the memory to extract net positive work while erasing and just sacrificing those correlations. So loosely speaking, we can think of entanglement here as sort of serving as a thermodynamic fuel together with the heat from the heat bath. In summary, we can use the information to turn heat into work, and we can also use work and information, including quantum information, including entanglement, as resources in both computation and thermodynamics. Does anybody have any questions about what I've said so far? Okay, I'll move on. Now that we've gotten a broad overview of some of the ideas behind quantum thermodynamics, I'd like to give a little taste of some quantum thermodynamics that's under active research in the subfield of quantum thermal machines. We'll talk about a quantum many-buddy engine. This many-buddy engine is based on the ability of particles to be in a certain phase of matter called many-buddy localization. And that has a horrible number of syllables. So sometimes I'll call it MBL. I try to avoid acronyms in talks, but I do need to introduce this one for reasons we'll see later. As I mentioned, many-buddy localization is a phase of quantum matter. For instance, suppose that you have a one-dimensional chain of qubits. We can label them from 1 to n. And we can impose on them a Hamiltonian that looks like this. First, there's a Heisenberg interaction, which means that sites j and j+1, nearest neighbors, will repel each other and also can flip in tandem. So one can flip downward while the other flips upward. Let's say that this happens with some frequency j. There's also a term that is called the disorder potential. You can visualize it as some very random background potential. For instance, if we're realizing this system with a bunch of ultra cold atoms, this could be imposed by an optical lattice. We can think of it as a magnetic field or field generally that points along the z direction. And we can construct it, for example, numerically as follows. So suppose that we want to find the value of the field at some particular spin. Then we'll pick a random number, h sub j, between -1 and 1, and multiply it by the overall disorder strength, little h. So that's how we construct this disorder potential. If in the lab, it looks like it's a dirty sample. It's random, it's not clean. And so you might think that such a system isn't useful, but it actually has a really interesting property. So suppose that the disorder strength is really large, much greater than the hopping frequency, and you measure the positions of the particles, and the particles will basically hang around in those positions for a long time. This is in contrast to very common behaviors. For instance, the behavior of an equilibrating gas. Suppose that we measure these particles' positions, and we find they're all clumped together in some corner of their container. Very soon after, they are going to be in very different positions. So this many-buddy localization is a special behavior. It's sort of a resistance to thermal equilibrium. We can say that many-buddy localization behaves athermally. Athermal systems not at thermal equilibrium relative to the environment, can serve as resources in thermodynamic tasks. We can understand this claim through a simple example that I learned in physics 43. Is that StatMech? Okay. Suppose that we have access to a heat bath, so a big environment at a temperature T sub h. And we're suddenly given a much colder system. We can let heat flow from one to the other. And from the heat flow, we can extract work. Work is useful. For instance, we can use it to power our cars. So it makes sense to think of the system not at thermal equilibrium relative to the ambient temperature as a resource. So can we take advantage of the athermality of many-buddy localization in a thermodynamic task? Well, of course, the answer is yes. Otherwise, I would not be giving this talk this way. And with some collaborators at Caltech, I illustrated the answer is yes by proposing the MBL mobile. This is why I had to use an acronym. It's a quantum many-buddy engine formed from a system that can be in the many-buddy localized phase. We designed an Otto cycle for it. An Otto cycle is similar to the Carnot cycle, which is more famous. It also consists of 4 strokes. And these are the cycles that operate in most car engines. So the 4 strokes include 2 isentropic ones. Who remembers what isentrope means? You in the back.
Means the entropy is constant.
Yes, constant entropy. Thank you. I think that's James. I can't see very well. Excellent. And there are also two isocores. This is tougher. What does isocore mean? Yes.
The same volume?
Same volume. Gold star. You guys are doing very well. Yes.
My ignorance of auto cycle 4 strokes, is that just gas powered or also electric?
The conventional auto engine does consist of an ideal gas.
But anyway.
So we usually draw out an engine cycle on, say, a pressure volume diagram. The pressure and the volume of this quantum Minibuddy system aren't the most relevant observables to us. So along this x-axis, I'll plot the ratio of the disorder strength to the hopping frequency. Remember, if the hopping frequency is much greater, or just the disorder strength isn't very large, then the system is just shallowly localized, particles can move around somewhat, or in an extreme, the system is in a whole different phase of matter. We can call this a thermal phase. It is characterized by particles and information spreading out very quickly. If anyone wants later, I can get more technical. If the disorder strength is very large, then the system is deeply localized. Along the y-axis, I'll sketch energies of our quantum Minibuddy Hamiltonian. And a really important difference between these two regimes consists of energy gap statistics, which come out of the following story. So I showed you a Hamiltonian on an earlier slide, but actually I showed you a form of a Hamiltonian. There can be many, many Hamiltonians that have this form, because remember H sub j, which was one part of the Hamiltonian, it determines the strength of the disorder potential on a particular site. That's a random variable. So if you take different samples of this random variable, you get different instances of the Hamiltonian. So really we're thinking about a whole class of Hamiltonians that share some properties. So suppose that you randomly pick a Hamiltonian from this class. It'll have some energy E around the middle of the spectrum. And right above that energy is a gap to the next energy in the energy ladder. What is the probability that that gap is of size delta? That's the quantity at the heart of energy gap statistics. And the seemingly innocuous quantity can have very different properties between these two regimes. We're going to take advantage of those properties, that difference. Yes?
So which distribution are you drawing this H over J from? So this gap would be determined by the probability distribution that governs this kind of rate, right?
Right. So I presented model Hamiltonian according to our favorite rule. We decided to draw little h sub j, the random variable between -1 and 1, according to, I think it was a uniform distribution. You could use a Gaussian distribution instead, but these microscopic details shouldn't affect the overall behavior of the whole Hamiltonian too much. The Hamiltonian will still be either strongly localized if the overall strength of the disorder h, little h, is very large, and if the overall disorder strength is not very large, the particles will be able to spread out more easily. And we're really interested in properties of all of the Hamiltonians that make systems very localized, or all the Hamiltonians that make systems not very localized. And there are lots of Hamiltonians in those classes. I just presented one example that's convenient. If the system is not very localized, then the energies will be roughly evenly spaced. Typical gaps are not far from the average gaps. The average gap, which I'll call average delta, I'll assume for convenience that that's constant across the cycle. And if the system is deeply localized, then these small gaps and large gaps occur much more frequently. We start off our cycle with the system shallowly localized and at thermal equilibrium at the temperature T sub h. So the system is described by this density operator, this quantum state. We can use the statistical interpretation of the density operator. We can imagine that in each trial, actually our system is on one particular energy level that's selected according to this canonical distribution. And then eventually we will average over all of these realizations. So at the beginning of our cycle, we disconnect the heat bath and we tune the Hamiltonian from shallowly localized to deeply localized. In a very simple approximation, we can suppose that the tuning is quantum adiabatic, very, very slow, so that the system is always on the same energy eigenstate. And that's only an approximation, so we can calculate corrections to it. The system is moving downward in energy space, and it's not connected to a heat bath. So according to the first law of thermodynamics, since what comes out is not heat, it must be work. So our engine performs work. And during stroke 2, we connect our engine to a cold bath whose bandwidth, WB, we ask be much smaller than the average gap. That means that this cold bath can exchange amounts of energy, only that are very small most of the time. This small bandwidth can connect the system only across these small gaps that are more common in the deeply localized regime. So the engine can drop across this small gap, sending just a small packet of information of energy into the cold bath. It can't drop across this large gap with high probability. During the next stroke, we tune back from deeply localized to shallowly localized. Again, the system moves downward in energy space. So again, it performs positive work. And then during stroke 4, we hook the system back up to the hot bath and we reset it to its initial state. So the engine on average absorbs positive heat. So during this cycle, we've traversed this trapezoid whose narrow snout is in the deeply localized regime. It's because we traverse the trapezoid in this direction that, just one moment, that the engine moves downward in energy space during the 2 tuning strokes, and so that it performs positive work. So we're taking advantage of how smaller energy gaps are more common in the deeply localized regime than in the shallowly localized regime. That's another way in which many-body localization is unlike a thermal phase. So this is one way we use the athermality of many-body localization. A question?
Yeah, so on the left, there's just, we're only seeing like 2 of these, but there's a whole bunch of like evenly spaced energy. And on the right, there's just 12 high probability of lots of smaller ones. And these cycles will have one on the shallowly localized state and one on the deeply.
Right, so I drew out a very special trapezoid. You can draw out all the possible trapezoids, and we did that. It's something to keep track of. The thing is, suppose that we started our cycle such that on the right-hand side, there's an actually big gap. It's bigger than the average gap. For instance, suppose we started our cycle here, so that we would go up here during stroke 1, and suppose that there's a big gap down here. Well, the cold bath cannot accept this much heat. So our engine is going to stay on this energy level throughout stroke 2. And during stroke 3, it's going to come right back down. So right. During stroke 1, the engine performs positive work. During stroke 3, it consumes that amount of work. So the net work is 0. And there are positive contributions to the work from these trapezoids. There are 0 contributions to the work from cycles like this. And then there are other variations that also don't detract from the average work. So on average across the whole spectrum, or approximately middle of the spectrum, the average work is positive. Yes?
Is there any connection of what you've shown to photosynthesis in the sense that, let's say a photon creates an electron hole pair in the beginning, and you take the excited electron very adiabatically down an electrical energy gradient. And so as it comes down, it can pump hydrogen ions, which is typically what happens in plants and other things. And then you lose that electron through a very slow chemical reaction. That's your right-hand side. And then again, you adiabatically send it through some electron transport complexes all the way back down to where it was low energy. And then you wait for the next photon from photosynthesis that comes in from the sun and light. So what I'm wondering is, have you tried, or has anyone else tried relating this to actual photosynthesis?
Not to my knowledge. It sounds interesting. So you would imagine mapping photosynthesis onto an engine cycle.
Yeah, so photosynthesis, what happens is the light comes and creates these electrons, excited electrons. And oxygen's involved in other complicated things, but the essence is what you're showing. The essence of it is that the excited electron is adiabatically sent down in an antenna complex. And plants are very careful about not doing it too quickly, because otherwise you lose energy if it's not adiabatic. And even mitochondria are very adiabatically moving electrons. There, they're getting the energy from the glucose rather than photons. But it looks like this is could also be a photosynthetic engine. That's my knowledge.
That sounds interesting. I imagine if anyone has done something on this, it's either Alanas Periguzic or Martin Plenio.
Okay.
But I'm not familiar with such a paper. That sounds interesting. There is a problem with this scheme. Suppose that we want to scale it up. So let's denote by n the number of sites. The size of the energy band, or the greatest energy minus the least energy, is proportional to the number of sites. But the number of energy levels scales exponentially with the number of sites. And so does the number of energy gaps in between the energy levels. So the size of the average gap decreases exponentially. And the size of the average gap we saw in the last slide is no more than, or is greater than the total average energy, or work outputted by our engine. And so in the thermodynamic limits, as the number of sites approaches infinity, the work output approaches 0, which doesn't sound very useful. We can resolve the problem by using that other athermal property of Minibuddy localization, namely localization. We can create some mesoscopic sub-engines of about 10 sites. The work outputted will be exponentially small just in this number. And then we can put a bunch of mesoscopic sub-engines next to each other to create one total engine. The total power will scale with the number of sub-engines linearly, or the total number of sites. So the total power will actually grow roughly linearly with the number of sites. We can put these sub-engines relatively close together, create a relatively high power density, because what happens in a sub-engine more or less stays in a sub-engine because of this athermal property of Minibuddy localization. The particles approximately stay put. So how do we evaluate an engine in physics 43 or in quantum thermodynamics? We calculate the power and the efficiency. It turns out that the average work outputted per cycle is proportional to the number of sites. It's proportional to the cold bath's bandwidth. And then there are some corrections because the cold bath isn't actually at 0 temperature. The hot bath probably isn't at infinite temperature. And I mentioned we're not actually going to tune the Hamiltonian infinitely slowly. So that's an analytical answer to this question. What is the power? But we can also estimate. We did some very rough order of magnitude estimates for an engine formed from silicon doped with phosphorus. This was used to realize a different type of localization, not quite Minibuddy localization, but the engine cycle can apply similarly. So the power turns out to be about 10 to the negative 16 watts. What does that mean? Well, we can compare it to the power of another small engine. It's about 10 times, according to our rough estimates, the power of the molecular motor that powers the flagellum of a bacterium. We can also estimate the power per unit volume, which is about 100 kilowatts per meter cubed. And what does that mean? It seems to be about a tenth the power of the engine in a car. So we're not going to have Minibuddy localized engines displacing our car engines in our garages anytime soon, but it's not too bad. Those are analytics and order of magnitude estimates. You can check these in simulations. For instance, my collaborator, Christopher White, simulated 10 qubits in a one-dimensional chain. So this was our prediction that the total average work is about like the cold bath's bandwidth. So along the x-axis, we have the cold bath's bandwidth in units of the average energy gap. Along the y-axis, we have the total average work in the same units. The red dots represent numerical data. The error bars are too small to see. The blue line is the theoretical prediction. And the gray region is the only region where we expect our prediction to work because the engine is in the right parameter regime that satisfies our assumptions. But the predictions work quite well outside of that regime. So much for the power. How about the efficiency? The efficiency is the work outputted over the heat absorbed during the stroke in which on average the engine absorbs a positive amount of heat. That turns out to be 1 minus the cold bath's bandwidth over twice the average gap. And we assumed that the cold bath's bandwidth was smaller than the average gap. So the efficiency can be somewhat close to 1. We should compare it with the efficiency of a conventional Otto engine. These two can equal each other. So first of all, what does this formula mean? So suppose that I'm a conventional thermodynamic agent with an ideal gas Otto engine. I compress and expand the gas between volumes V plus and V minus. And this gas has heat capacities at constant pressure and constant volume, C sub P and C sub V. So suppose that, what does this equality mean? Suppose that I have this ideal gas heat engine and it has these heat capacities. I choose 2 volumes between which to expand and compress it. Then I can hand my numbers over to Billy. Suppose that Billy is a quantum thermodynamic agent. He has an NBL mobile Otto engine. Then he can choose a cold bath bandwidth and an average gap such that ideally his engine achieves the same efficiency. Both these efficiencies are no more than the Carnot efficiency, which is an upper bound on the efficiency achievable by any heat engine that runs between just 2 baths of 2 different temperatures, which is good because if we break the Carnot bound, we have broken the second law, which probably means we're wrong. The NBL mobile has a few advantages over some particular competitors. We saw that it can scale relatively robustly because of its localization properties. And relatedly, it can achieve a somewhat high power density relative to, for instance, a system that doesn't have this localization. Also, if you run an engine enough times, then you will see fluctuations between the amounts of work that it outputs from trial to trial. We want for the fluctuations to be small so that our engine is reliable. And our engine is relatively reliable compared to a particular competitor. I think I won't take the minutes now to explain, but if you want to know, let me know later. So there are relatively few fluctuations because of that other athermal property of Minibuddy localization. Its energy gap statistics are quite different from the energy gap statistics of that more thermal regime of matter. For the same reason, there are relatively few worst case trials. If you run your engine enough, then eventually in some trial, it will absorb net positive work. I call this a worst case trial. And there are relatively few of those also because of non-thermal energy gap statistics. What is ahead for quantum steampunk? I'll skip this and just focus on quantum steampunk broadly. I think that one of the most interesting opportunities is to bring quantum steampunk outside of itself as a field to interact with other disciplines. So quantum thermodynamics is an extremely rich field. It has lots of different subfields. I give a taste of one, quantum thermal machines, but there are many more. However, the whole landscape of quantum thermodynamics itself is embedded in a much larger landscape in which plenty of people are interested in different ways in quantum physics, information, and energy. So we can sometimes use our toolkits to answer pre-existing questions in other fields, or we can use inspiration from other fields to ask questions about quantum thermodynamics. There are great toolkits, especially for studying many-body thermalization, quantum many-body thermalization in condensed matter, atomic, molecular, and optical physics, and high-energy physics. But we can integrate our toolkits, use one toolkit to deal with the other's problems. Another important opportunity now for quantum thermodynamics consists of experiments. Traditionally, for decades, quantum thermodynamics was very heavily theoretic. But we have great control over quantum platforms now. Some people in this room have great control over quantum platforms. So we can use them to test quantum thermodynamic predictions. And I think that a really important challenge, including for theorists, is to come up with predictions that we really need experiments for, that we can't just solve on a computer. Well, a classical computer. So in summary, we saw that quantum information theory serves as a toolkit for reimagining the thermodynamics of the Victorian era for today's physics. We saw that we can use information such as entanglement and work as resources both in information processing and thermodynamics. We saw one example of an active research subfield within quantum thermodynamics, quantum many-body engines. We illustrated with the MBL mobile. We saw that many-body localization can be thought of as an athermal phenomenon, and so can serve as a resource in a thermodynamic task. We saw an Otto cycle for this many-body engine. We evaluated it in terms of its power and efficiency. And we saw that there's really a lot to be done in quantum thermodynamics. It's a field that's started booming over the past few years. So it has a lot of, no pun intended, it really does have a lot of energy. In case you're hooked, I recommend these two reviews. The field has been moving very quickly, and these papers were originally written in 2015. So a lot has happened since then, but they are great overviews of the field as a whole. And also there is another reference coming out soon. I wrote a book for the general public about this field of quantum steampunk, but it's supposed to be fun for physicists too. And it features Thorstens and jokes. So if you read the book, count how many you can recognize and then email me. I'm curious how many he reuses. Again, if you take quantum information theory from the 21st century and use it to reimagine the thermodynamics of the 1800s, then you get this wonderful, exciting blend of old and new that has all the romanticism and nostalgia that I call quantum steampunk. Again, steampunk fans dream it, quantum information thermodynamicists live it. Thank you.
Thank you for that wonderfully rich and energetic talk. So are there any questions? Ryan.
Well, thank you very much for that. I have a question about the simulation. Thank you. I have a question about when you were showing the predictions of the amount of work relative to the gap sizes, and there was a simulation that you were comparing a simple analytic prediction to. And you mentioned that you would expect it to work only when the gap sizes are relatively small, but actually in the simulation it looked like it matched almost perfectly, like all the way out to significantly larger ones. And I'm just wondering, why does this work? And if we understand that, yeah, this one right here. If we understand that, why does it, does that mean that the applications of this may even be more varied than what you were suggesting?
The calculation was a perturbative one. So we considering how typically on the left-hand side here, we'll have a gap that's sort of like the average gap. We actually wrote out the probability distribution and expanded the probability distribution in our small parameters. And we did something similar here. And the positive non-zero contributions to the average work tend to come from these small gaps on this side, but those aren't the only contributions. For instance, you could have a chain of 2 small gaps such that the whole thing lies within the cold bath bandwidth. Or you could have 3 or 4 even, they're just rarer. So we didn't include them in our calculation. So there are corrections like that that I think account for the unexpected agreement.
Any other questions, Jack?
Hi, thanks for the talk. It seems like the most important thing that makes the auto cycle work is that you can take it from something with evenly spaced gaps to like not evenly spaced gaps and tune it like that. And I was wondering, if that was like the main, if I was right that that's like the main thing that makes this work, and also what if you said a little bit about why localization is also important. And I was wondering if you could just explain why that part of this particular state is also important, not just the tuning of the energy.
The localization enables us to scale up. So we can make these mesoscale subengines and put them relatively close together because we don't fear too much that particles from one subengine will stray into another and interfere with it. So this enables us to achieve a reasonable power as we scale to larger and larger system sizes. And again, compared to certain competitors, a relatively high power density. And yes, the key that makes the auto cycle work separately from this point is the difference in the energy gap statistics. So how the energy gap statistics of the Minibuddy localized regime are quite different from the energy gap statistics of the thermal regime. The thermal regime has more evenly spaced levels, and the deeply localized regime has more small gaps. That really is the key that you pulled out.
So I have a question. I actually have 2. And first, thank you. Wonderful talk. I kind of knew it was going to be, and I'm glad that we're not disappointed. So my first question is perhaps slightly at the beginning of your talk, you mentioned Landauer's principle about how much entropy it requires to race a bit. I was wondering how close are we to actually reaching that limit?
How close we are to
actually reaching Landauer's limit for erasure? So I am to understand that in semiconductor technology, this is not even close. So.
There have been proof of principle experiments that show that if you erase more and more slowly, then you do approach work of KBT log 2. So there are proof of principle experiments there. Technologies are not, that it is, and the Landauer regime is not relevant to today's technologies as they actually operate outside of proof of principle experiments.
Okay, excellent. I had one more question, and this one's a little more in the heart of your talk. So you talked about this diagram of extracting work from the cycle. So in the cycle, normally when we think about this inside of a normal thermodynamic picture, we have a PV diagram. And so the area naturally corresponds to energy quantity. Is this similar here? Is there a way to actually get some interpretation of what that area inside that plot means, or is it just a sketch?
So it's more, in this case, the change in the y coordinate that corresponds to the work, because we chose for our y-axis to consist of the energies, just because this is the way that we found that we could draw it that was useful for us. So when we go during this stroke from up here to down here, there's this change in y, which corresponds to a change in the energy. And when we go during stroke 3 from down here to down here, that change is a change in energy. So we were more using the y coordinate as our energy coordinate rather than the area. But I agree, the convention, we're used to seeing engine cycle diagrams in which area corresponds to energy. This quantum many-body system, has different observables and properties that are more useful for us to think about, or at least the way we were thinking about it.
So I just propose one last question, and then we have a discussion or tea afterwards. More on that in a moment, but maybe to Daniel.
Thank you. So I was wondering if there are prospects for speeding up the isentropic branches of the cycle. You mentioned, like, especially towards the localized regime, the equilibration time, thermalization time becomes longer and longer.
Right.
It seems like a challenge if you're trying to map states from one, the shallowly localized phase into sort of these random states in the localized regime.
Right.
Like, are there speed up prospects for that sort of branch?
Yes, you're right that this thermalization in the deeply localized regime is what sets the time scale for the cycle. And we were actually pretty surprised that we found that this does work, that there is some portion of parameter space in which this can perform net positive work. So it was hard enough to show that it works. We definitely did not optimize it. And so we believe that that is possible. The optimization of the thermalization over here could depend on your platform. And so how you can create this cold bath and how it can interact with your engine. Also, the tuning strokes might be optimized. So there are techniques in quantum computation and thermodynamics and elsewhere, shortcuts to adiabaticity that enable you to change the Hamiltonian quickly while in some ways achieving the same effects as a slow tuning. They might cost work, which might be inconvenient, but maybe in this case, it could potentially be less work than you would get out of the cycle. That could be checked. And I'm not sure if shortcuts to adiabaticity have been developed for many-body localization, but they could.
So let's thank Nicole once again for a wonderful talk. Again, just a reminder, we have tea, I believe. I haven't actually